Good day, everyone. I am candidate number 5, Sarai Hanalet Grace G, together with candidate number 14, Lazara Chinian L. Today, we will be discussing about the mathematicians in the 17th century. So here is our objective. First is we will explain the importance of mathematics in the 17th century. And second is we will identify the key contributions of the 17th century mathematicians. And lastly is we will describe how 17th century mathematics shape our mathematical concepts today.
Before we proceed to the mathematicians themselves, let me first give you a brief overview of what mathematics was like during the 17th century. Mathematics in the 17th century is known as the age of the scientific revolution. It is called the age of scientific revolution simply because during this time, the way people understand the world began to change. Instead of relying only on old beliefs or traditional explanations, scholars started to use reason, observation, and experiment to learn new things, and also to discover how the world truly worked. During this period, mathematics became very important. It is not just a study of numbers, but also a powerful tool to understand nature and support scientific discoveries. Because of this, math began to influence science, engineering, physics, and psychology. Schools also started to treat mathematics as a subject that develops logical thinking and problem-solving skills, which is we use today. The first mathematician we will discuss is René Descartes, who lived from 1596 to 1650 and is famously known as the father of analytic geometry. Descartes was born on March 31, 1596 in a town called La Haye-en-Touraine in France. In honor of his contributions, the town was later renamed Descartes. He was not only a mathematician but also a philosopher and scientist, and his work had a major influence on modern mathematics and philosophy. Descartes studied at the Jesuit College of La Flèche, which was one of the best schools in France during his time. There, he learned classical subjects such as grammar, logic, and philosophy. But he also developed a strong foundation in mathematics. This foundation became the main focus of his intellectual life and led him to make revolutionary contributions in both geometry and algebra, as well as in the way we use mathematics to understand the world. René Descartes died on February 11, 1650 in Stockholm, Sweden. His ideas continued to shape mathematics and philosophy long after his lifetime. Now, we will proceed to René Descartes' contributions to mathematics. First is the analytical geometry. During the 17th century, mathematics was undergoing major changes. Algebra and geometry were treated as two separate branches. Geometry dealt with shapes and diagrams, right? Well, algebra used symbols and equations. But Descartes has made a major achievement. It was to combine these two fields into one system, which is now known as the analytic geometry. Wow, Descartes is so amazing. He combined the two branches. So, analytic geometry is Descartes' most important work in mathematics that is found in his book La Géométrie, which is it published in 1637. In this book, he introduced the revolutionary idea of representing geometric figures using algebraic equations. For example, instead of drawing a circle, we can describe it with an equation x squared plus y squared equals r squared. This approach allows mathematicians to study geometric shapes using numbers and equations, which was a completely new way of thinking at that time. By merging algebra and geometry, Descartes opened the door to modern mathematics, including calculus, physics, and other scientific applications. The second contribution of Descartes to mathematics is the Cartesian coordinate system. I know that we are all familiar of this because we already tackled this one on our previous year. The Cartesian coordinate system is a fundamental concept in mathematics that allows us to locate points and draw graphs on a flat surface called a plane. It consists of two number lines that intersect at a right angle. The x-axis runs horizontally. X-axis runs horizontally, which is left to right, while the y-axis runs vertically, which is up and down. The point where they intersect is called the origin. Each point in this system is represented by an ordered pair, x and y, where x shows how far the point moves horizontally from the origin, and y shows how far it moves vertically. This system was introduced by René Descartes, a French mathematician and a philosopher. The name Cartesian comes from the Latin form of his name, Cartesius. And the Cartesian coordinate system made it possible to connect algebra and geometry, leading to the development of analytical geometry. It is widely used today in mathematics. So we use this in mathematics for graphing equations and analyzing shapes, and also in engineering to model physical systems, and in computer graphics for creating digital images and animations, and also in GPS and navigation system to locate positions on maps. So in summary, the Cartesian system gives a precise way to describe any point in space using numbers. The third contribution of Descartes to mathematics is the use of variables in algebra. René Descartes also played a major role in standardizing the use of variables in algebra. He introduced a clear system for using letters to represent numbers in equations, such as the x, y, and z represent unknown values, or the numbers that we need to find. And the a, b, and c represent known or the given values, and it considered as the constants or the coefficients. For example, in the equation ax plus b equals c, where a and b are the known numbers, and the x is the unknown value to be solved. This simple notation made algebra more organized, logical, and easier to understand. It also allowed the mathematicians to express general relationship instead of just specific numerical examples. And the fourth contribution of Descartes to mathematics is the role of a science. The role of a sign is a principle used in algebra to help determine the number of positive and negative real roots of a polynomial equation. It was also introduced by René Descartes and is often referred as Descartes' rule of signs. So here is how it works. Look at the signs and the coefficient in the polynomial, for example, the positive and negative. The number of signs changes in the sequence of the coefficients tells you the possible number of the positive real roots. To find the possible number of the negative real roots, substitute negative x for x in the polynomial and count the sign changes again. So example of here is if you have the polynomial fx equals x cubed minus 4x squared plus 5x minus 2, is the signs are the positive, positive, and also negative. So there are three sign changes, meaning there could be 3, 1, or 0 positive roots. The number always decreases by even numbers. This rule doesn't give the exact roots but help predict how many positive or negative solutions exist, which is a powerful tool when analyzing polynomial graphs. Today, the rule of signs remains an important technique or teaching tool in algebra, helping students understand the behavior of polynomial functions and their graphs. Let us proceed to Descartes' contributions to philosophy. Descartes is famous in mathematics, but Descartes is also made a major contributions to philosophy. He believed that human reason is the foundation of knowledge. He introduced the method of systematic thought, questioning everything until he found something that could not be doubted. This led to his most famous philosophical statement, which is the cogito ergo sum. The meaning of this is I think, therefore I am. Because of his influence, Descartes is also called the father of modern philosophy. The second mathematician we will discuss is Pierre de Fermat, who lived from 1607 to 1665 and is famously known as the father of modern number theory. Pierre de Fermat was one of the most influential mathematicians of the 17th century, earning the title Father of the Modern Number Theory for his groundbreaking work on the properties of integers. He was born sometime between October 31 and December 6, 1607 in Benimont de Lomange, France. Unlike many of his contemporaries, Fermat was not a professional academic. He worked as a lawyer and government official in Toulouse, while pursuing mathematics as a personal passion. Despite not being a full-time scholar, he pursued mathematics as a passionate hobby, producing groundbreaking results that would shape modern mathematics for centuries. His work profoundly shaped number theory, geometry, probability, and the foundation of calculus, leaving a lasting legacy in mathematics. Fermat died in 1665 at the age of 57, yet his discoveries continue to influence modern mathematics, science, and technology. Now, we will proceed to Fermat's contributions to mathematics. First is number theory. Fermat is often called the father of modern number theory because of his groundbreaking work on the properties of whole numbers. Number theory, sometimes called the higher arithmetic, it deals with the study of integers and their relationships. Fermat made several significant contributions, including the Fermat's Little Theorem. This is a fundamental result in modular arithmetic and is widely used in cryptography today. And next is the Fermat numbers. Fermat studied numbers of the form Fn equals n raised to the power of n raised to the power of n plus 1. He conjectured that all such numbers were prime, although this was later found to be true only for his first few cases. And lastly is the 2-squared theorem. Fermat provided that a prime number of the form 4k plus 1 can express as the sum of two squares. And the next contribution of Fermat is the Fermat's last theorem. It is also in the number theory. Perhaps his most famous contribution, Fermat conjectured that the equation x to the power of n plus y to the power of n equals z to the power of n has no whole number solution for n less than 2. Fermat's last theorem remained a mystery for over 350 years. In the margin of his copy of an ancient Greek text, Fermat wrote, "I have discovered a truly marvelous proof, but this margin is too small to contain it." The theorem puzzled mathematicians for centuries because Fermat never published a proof. It was finally proven in 1994 by a British mathematician, Andrew Wills, using advanced concept in algebraic geometry and modular form. The theorem is now celebrated as a landmark in the history of mathematics due to the ingenuity required for its proof. We will now proceed to the third contribution of Fermat to mathematics. This is the analytic geometry. Fermat worked independently of René Descartes to develop the methods of analytical geometry, which combine algebra and geometry. I already discussed this one to René Descartes' contribution. Analytic geometry allows geometric shapes such as curves to be described using algebraic equations. We will proceed now to the fourth contribution of Fermat. It is the foundation of calculus. Before Newton and Leibniz formalized calculus, Fermat was already studying maxima and minima, finding the large or the smallest values of functions, tangents to curves, determining slopes of curves at specific points. His method anticipated some of the basic principles of differential calculus, providing tools for studying rates of change and motion. And the last contribution of Fermat is the probability theory. Fermat collaborated with Blaise Pascal to develop the early theory of probability, a branch of mathematics concerned with measuring uncertainty. Their work originally focused on games of chance, such as dice and card games. They developed methods to calculate the likelihood of different outcomes, laying the groundwork for modern probability and statistics. This collaboration marked the first systematic attempt to apply mathematics to real-world uncertainty. In summary, Fermat's contributions span a remarkable range of mathematics, from abstract number theory to the practical probability, and his ideas influenced the development of calculus, geometry, and modern mathematical thought. His work shows both the depth and breadth of 17th century mathematical innovation. We will now proceed to the third mathematicians, which is Blaise Pascal, who lived on 1623 to 1662. Blaise Pascal was a French mathematician, physicist, inventor, and philosopher. Pascal was born on June 19, 1623, in Clermont-Ferrand, France. His childhood was marked by both tragedy and opportunity. When he was only 3 years old, his mother passed away, leaving him to be raised by his father, Étienne Pascal. Étienne was a tax officer but also had a strong background in mathematics, which greatly influenced Blaise's education. Instead of sending him to formal school, Étienne decided to teach his son at home. Wow, he is the one who teach his son, which it provide him with a focus and intellectually rich in in learning environment. From a very young age, Blaise Pascal showed remarkable intelligence and curiosity, especially in mathematics and science. His father noticed his natural talent and nurtured it carefully. By the time Pascal was a teenager, he was already solving complex mathematical problems and conducting experiments on his own. His exceptional ability to lead his father to introduce him to some of the most prominent scientists and mathematicians of the time. Pascal family later moved to Paris, the center of learning and scientific progress in France. There, young Blaise met and learned from well-known intellectuals such as René Descartes and member of the Académie Française, a group of scholars devoted to scientific inquiry. This environment helped shape Pascal's thinking and inspired him to explore ideas in geometry, probability, physics, and psychology. Pascal died in August 1662 in Paris, France, at the age of 39. He's too young. Even though he lived a short life, Pascal's intelligence, creativity, and faith left an enduring legacy. His ideas continue to influence mathematics, physics, computer science, and psychology even today. Here are Blaise Pascal's contributions to mathematics. First is Pascal's triangle. One of Pascal's most famous contributions to mathematics is Pascal's triangle. This is a triangular arrangement of numbers where each number is the sum of the two numbers directly above it. It begins with a single number 1 at the top, and each subsequent row increases in length. For example, is first row is 1, the second row is 1 and 1, and the third row is 1, 2, and 1. And the fourth row is 1, 3, 3, and 1, and the fifth row is 1, 4, 6, 4, 1. I will explain it more. So first row is 1, and the second row is 1 and 1. So 1 plus 1 equals 2. Since it said that the sum of the two numbers directly above it. So 1 plus 1 is 2. And the next row is that 1 plus 2 is 3. And the next is 2 plus 1 is 3. And the next row is 1 plus 3 is 4. So we will put 4 here. And next is 3 plus 3 is 6. And next is 3 plus 1 equals 4. So center is 6. So yes, that is how Pascal's triangle work. The sum of the two numbers directly above it. I guess it is already explained by some of the reporters of the previous topic. So let us proceed to here. Each row in Pascal's triangle represent the coefficients of the binomial expansion a plus b, and for instance, in the expansion of a plus b squared equals a squared plus 2ab plus b squared, the coefficients in 1 is 1, 2, and 1 and can be found in the third row of the triangle. Similarly, the coefficients for 1 plus b cubed is 1, 3, 3, and 1. It appears in the next row. Pascal's triangle has many important applications. It is used in algebra to expand binomial expressions easily, in combinatorics to calculate the number of possible combinations, such as n choose r, and in probability to determine the possible outcomes of events. It also appears in patterns such as Fibonacci numbers and fractals, showing its deep connections to nature and mathematics. While similar number triangles appeared earlier in China, known as Yang Hoi Triangle, and in India, Pascal still the one the f- that the first to connect it systematically to algebra and probability theory. So Pascal is really the one who contribute the Pascal's triangle. His clear expansion and application of the triangle made it one of the most valuable tool in mathematics and a lasting symbol of his genius. So next is we proceed to the second contribution of Pascal, which is it is the probability theory. Pascal is widely recognized as one of the founders of the modern probability theory in the 1654. He exchanged a series of letters with another great mathematician, Pierre de Fermat, to solve a famous gambling question known as the problem of points. The problem asked how to fairly divide the strikes of a game that was interrupted before earlier player had won. Through their discussions, Pascal and Fermat developed mathematical methods to calculate the likelihood of different outcomes. This was the beginning of a new branch of mathematics, probability theory, which studies chance, risk, and uncertainty. Their work established the concept of expected value, which is still a fundamental idea in statistics and decision making today. The development of probability theory had a profound impact on many areas of modern life. It laid the foundation for statistics, insurance, economics, and risk analysis. It also plays a key role in data science, artificial intelligence, and weather forecasting, where predictors are made using probabilities. So in summary, Pascal's work on probability transformed not just mathematics but the way we understand and predict the real world events. The third contribution of Pascal to mathematics is the projective geometry, or the Pascal's theorem. Another remarkable achievement of Blaise Pascal was the projective geometry, a field that studies the properties of geometric figures that remained unchanged under projection. Amazingly, Pascal made his major discovery in the area at just 16 years old. In 1639, he discovered what is now called the Pascal theorem, or the hexagrumum mysterium theorem. The theorem states that if a hexagon is inscribed inside any conic sections, so what is conic section? Conic section such as the circle, ellipsis, parabola, and hyperbola, the 3 points where the opposite sides meet will always lie on a straight line. This straight line is known as the Pascal line. Pascal's theorem was a groundbreaking discovery because it connected the geometry of conic sections with deeper mathematical structures. It laid the groundwork for the later development for projective geometry, a field that explores how shapes and figures appear when projected onto different surfaces, and essential to concepts used today in architecture, art, computer graphics, and engineering design. His work on geometry demonstrated not only his talent for abstract thinking but also his ability to link different branches of mathematics into a unified understanding of space and form. So let us proceed to the fourth contribution of Pascal. It is the foundation of calculus. Although Pascal did not create calculus himself, his early studies made important contributions towards its development. During his lifetime, mathematicians were trying to understand infinite processes in the calculation of areas and volumes, problems that later became central topics in calculus. Pascal studies the areas under curves, the of infinite series, and the properties of curves generated by ruling circles, known as the cycloids. He developed methods for finding volumes and surfaces of revolution, which were essential ideas later used by Isaac Newton and Gottfried Wilhelm Leibniz in their formulations of infinitesimal calculus. His investigation of continuous change, motion, and infinite division helped prepare the ground for the birth of calculus. Today, calculus is used in physics, engineering, computer science, economics, and countless other fields. And Pascal's early insights played a vital role in its foundation. So, in summary, Blaise Pascal's contributions to mathematics were extraordinary and far-reaching. His Pascal's triangle gave mathematicians a simple yet powerful tool for algebra and probability. His work with Fermat on probability theory established a completely new area of mathematics that influenced science and technology even today. And his discovery also in projective geometry showed his early brilliance and creativity, and his work toward calculus led essential groundwork for later generations of mathematicians. Pascal's ideas not only advanced mathematics but also shaped the modern world understanding of logic, probability, and the nature of numbers. Even centuries after his death in 1962, his name remains one of the most respected in the history of mathematics. Let us proceed to Pascal's scientific and technological contribution. Blaise Pascal was not just only a brilliant mathematician but also an innovative scientist and inventor. His discoveries in physics and engineering had profound effects on both science and technology, influencing tools and machines that we use even today. Two of his most notable contributions in this area are the Pascal's law in fluid mechanics and the invention of Pascaline, an early mechanical calculator. So first is the Pascal law, or the fluid mechanics. One of Pascal's most important contributions to physics is the Pascal's law, which he discovered while studying fluids. The law states that pressure applied to a confined fluid is transmitted equally in all directions. This simple principle has a far-reaching implication in engineering and technology. It forms the basis of hydraulic system, which use fluids to multiply force and perform work efficiently. So, modern application of the Pascal's law are the car breakers, hydraulic lifts and jacks, and also the pressurized system. So, next is the Pascaline, or the mechanical calculator. At just 19 years old, Pascal invented the Pascaline, one of the world's first mechanical calculator. He decided to help his father, a tax officer, with the tedious task of performing complex addition and subtraction. The machine used a system of gears and wheels, allowing numbers to be entered and calculations to be performed mechanically. The Pascaline is considered a precursor to modern computer. It introduced the idea that calculations could be automated, a concept that eventually led to the development of electronic computing machine centuries later. In honor of Pascal's contributions, the Pascal programming language was named after him, highlighting the lasting influence of his work on both technology and computer science. The Pascaline exemplifies Pascal's ability to combine mathematical knowledge with practical invention, making everyday tasks more efficient and laying the foundation for modern computing. We will proceed to Pascal's philosophy and later life contributions. Later in life, Blaise Pascal's focus shifted from mathematics and science to religious and psychology, influenced in part by ongoing health problems that affected him throughout his life. So, despite his physical struggles, he produced some of the most profound philosophical writings of the 17th century. Pascal's most famous work is the Penses, or Thoughts, is a collection of reflection on faith, human nature, and the relationship between reason and belief. In it, he explores themes such as the fragility of human, the limitations of reason, and the pursuit of happiness. Pascal sought to understand how humans could reconcile rational thought with spiritual belief, presenting his ideas in a way that continues to influence philosophy and theology. One of his best-known philosophical contributions is the Pascal's wager, an argument regarding belief in God. He proposed that even if the existence of God is uncertain, it is irrational to believe in God, because the potential benefits of belief or the internal happiness far outweigh the potential cost of disbelief. So, Pascal's later life were marked by intense reflection and devotion. He continues to study and write, balancing his contributions to mathematics and science with a profound engagement in spiritual and psychological inquiry. That would be all. Thank you for listening.